Good afternoon, everyone, and welcome to Permian Tech Talk. Thank you for joining us. We are thrilled to have you here as we continue this journey of knowledge sharing and industry collaboration. As the moderator of this session and Pio Petros Business Development Manager for North America, I'd like to introduce myself. My name is Jamana Abdurazek. I hold a Master of Science in Petroleum Engineering from the University of Houston, and I'm currently an Engineering Project Manager at Logan Associates. It's my pleasure to be moderating this session with you today. Now I'm honored to introduce our speakers, James Evans and Anthony Sisto, the President and Vice President of Specialized Desanders. They will be discussing desanding without compromise, high range, zero emission performance in this session. For those unfamiliar, Specialized Desanders is a rising company in solids management technology, helping operators safely and efficiently remove sand from production while maintaining optimal flow performance. Their zero emission, high capacity solutions not only protect equipment and reduce downtime, but also deliver cleaner, safer, more sustainable operations. Throughout this session, we encourage you to submit your questions in the chat box and we will address as many as possible. Please note that this session is being recorded and will be uploaded to our YouTube channel, Pio Petro. If you haven't already, we invite you to subscribe to our YouTube channel and follow us on LinkedIn at Pio Petro for updates and upcoming courses and forums. With that, please join me in giving your full attention to our esteemed guests, James Evans and Anthony Sisto. Welcome, guys. Thanks for joining us today. We are so glad to have you on Permian Tech Talk.
Good afternoon. Thank you, Joanna. And thank you, Ahmed and Pio Petro, for inviting us to this talk. I think you just took my entire speech out of everything that I was going to say. But James Evans, President, Specialized Desanders. I've been with the company just over 18 or just about 18 years now. Throughout those 18 years, I've seen many changes within the company and numerous changes throughout the world and the oil and gas environment. With me today, who will be getting into the more technical side of things, is Anthony Sisto, our VP of US and Marketing Sales in the US. When the company was founded back in 2001, the original founders had built and designed and built a patented Desander, which originally was only 8 inches OD, 10 feet long. And over the years, we've been able to design and build pressure vessels, Desanders, to all the way up to 24 inches in OD, 20 feet in length. Being able to handle some of the most harshest conditions throughout multiple basins. Specialized Desanders is an engineering company. First off, we look at the challenges to do with sand particles in the harsh environments. We're able to provide a solution to E&P companies, flowback companies, and multiple partners that we have throughout the industry, allowing them to work on some of their challenges of reducing costs, reducing manpower, but while increasing safety for what they are required. So over the years, we've seen and developed multiple things within the company. We developed a sand monitoring system, which we call the Sand Sentry, which provides a real-time sand monitoring solution, which allows the E&P company or operators on location to see how much sand is being captured, which then they can use that data further into designing their completions, their flowbacks, almost anything that they particularly want to use that information for. So over the years, as I mentioned, we've built small vessels. We've increased our bigger vessels into harsher conditions. Throughout those years, we've had a couple of different partners. Originally, we started with just 3 small private founders, and then today we are sponsored by Morgan Stanley Energy Partners, who continues to help us develop and build the company, allowing us to work in some of the most challenging basins, one of them which being the Permian Basin. Since that's what we are talking about today. We've been down in the Permian Basin for over eight years now, working with some of the clients and flowback companies down there, working in some of the most harshest and challenging environments. One of our recent successes, or a couple of recent successes over the years, is back in 2024, we built our 1,000 Desander within the company. We do sell and have a rental fleet, but we were able to build 1,000 Desanders within the company. One of our most recent successes in the Permian Basin, we were partnered with an E&P company and a flowback company, and we were able to do a zero-emission flowback, which allowed the E&P company to actually sell their gas rather than vent it or flare it off into the atmosphere. So a few highlights about the company there. I will turn it over to Anthony Sisto to get down into some of the more technical details of how our operation works.
Excellent. Thank you, James. So yeah, it really is a story of growing with the needs of the industry. So when we started the company, we were focused on formation sand, small amounts of sand over a long period of time. With the industry evolving, longer laterals, hunter mesh, so many different things to try to get the very most out of unconventional reservoirs. Our desanders needed to grow, our company needed to grow, and we needed to meet the needs of the industry in a number of technical ways. I tell people we're a technology company, we're an engineering company, and the problem we've chosen to solve is sand production during flowback, initial production, and really throughout the life of oil and gas wells. So I thought I'd start by kind of defining the problem, which is sand production at various phases throughout the life of the well. So looking at some of those phases, we have flowback, which can be characterized as the first maybe 6 weeks to 6 months that the well is turned into production. That can be characterized by higher sand rates for sure, anywhere between 15 and 1,500 pounds per hour. Total amounts of sand could be upwards of 75,000. We've actually seen more than that here in the recent past. And really, it's a matter of what's the well going to bring to surface, and you really don't know until you get going, and a lot of it is dependent on how things are managed on location. So that sand production can be characterized as semi-consistent. You can sort of know what to expect, but it is going to be unpredictable in some capacity as well. During that phase, there's a potential for damaged flowback iron, sand-related shut-ins, which can be very detrimental to the productivity long-term of your oil and gas wells. If you're not able to get up to rate and clean up that well in that first initial production phase, then a lot of times that cleanup will be inefficient and production will suffer long-term. Ability to achieve those target rates and perform that for that well to perform the way reservoir and production engineering would design can be hindered by sand production unless you have means of managing it at the surface during that phase. Moving into initial production, this is post flowback. A lot of times this is characterized with manpower being released from location, and those sand rates come down now into the single digits. And on scale, it could be a lot less sand at lower concentrations. But in turn, some of those lower pressure flows are at higher velocity, meaning that damage to facilities and production equipment, now that flowback is released, now becomes a more critical issue. That can result in uncontrolled releases or downtime, increased maintenance costs, and again, performance of the well and production can suffer. That sand production is semi-inconsistent. New zones contributing, meaning sand slugs coming when you least expect it, and then not having manpower on location can exacerbate the problem in that now you don't know what has happened until it's too late. Long-term production, we're looking at 0 to 2 pounds per hour, depending on the formation, the area, the wells themselves. You can clean up completely. Some wells never clean up completely and are always going to have that nuisance sand that comes back at very low concentrations. Minimal overall sand production. Sometimes facilities can handle it, sometimes they can't, and it also is unpredictable. But periodically, facilities will need to be cleaned out. There'll be unplanned shut-ins, alarms, wells that ESD unexpectedly in the middle of the night, things like that on account of sand that's not managed at surface, and then the maintenance and repair costs due to the erosion of surface equipment and even pipelines in some capacity. The factors that affect how much sand each well is going to bring back are really multifaceted, in that it can have to do with your frac, the sand size and quality. Like I mentioned, the more 100 mesh that's pumped, obviously the smaller sand particles have a higher propensity to come to surface. Stage spacing, amount of sand loading in each of those stages, and then the fluid system and how that's managed can also play a part in how much sand is going to come to surface. Now, we're talking about millions and millions of pounds of sand going into the well. Sometimes we're seeing as little as 0.1% or less of that frac job. Still, at those numbers, tens of thousands of pounds of sand at high velocity can cause a huge issue when it comes to the integrity of facilities, equipment, and operations on site. Looking at some other factors, which direction the well is drilled. Obviously, sand can roll downhill easier than it can be pushed uphill. And then the completion tools, dissolvables, different drill out efficiency parameters, and whether or not the well was cleaned up well in the first place. And then, are you being aggressive with your flow back? Are you opening the well quickly, or are you taking it easy? Really bringing that well into production slowly. All those things don't necessarily mean that less sand will come to surface, but it does indicate how fast, how much sand would come in that initial production phase, and what you need to be ready for. And then whenever artificial lift is installed, changing downhole dynamics, lowering bottom hole pressures, different cycling or other artificial lift mechanisms can destabilize sand that's in the formation or in the lateral, and you start all over in a way with sand production that starts to come to surface later in the life of the well. So anytime anything changes, or if a well's shut in for an extended period of time and then brought back into service, then now you have another chance for sand to cause an issue and come up the well bore. Let's get that here. So looking at various sand control equipment and technologies that are on the market, obviously this is an evolving space like every other technology space in the industry. But the initial way to handle sand was with a vertical sand separator, traditionally an impingement style where there was a plate inside. A lot of these were built, early on in the in the industry with fracking or with formation sand, and they were notoriously inefficient, talking about maybe 50 or 65% efficiencies. The industry has gone to more of a cyclonic function that uses a differential pressure to spin the sand basically out of the fluid, push it to the wall of the unit where it then falls. That can be more efficient, maybe upwards of 80%. That space continues to get more and more advanced, and companies are pushing the boundaries of what they're able to do there. That being said, the vessel itself looks similar in that it's in a vertical orientation. Some vessels on the market are spherical. This can be a benefit in that they maybe hold more sand, they have higher sand holding volumes. They both blow down on the fly, meaning while the well is flowing, you're going to be flowing that well to an open top tank that would evacuate the vessel as much as they can, and then on the fly that sand is taken out of the flow stream. How often you blow down those vessels really has to do with a kind of a guess and check method. How much sand is in there. If it's a lot, we blow down more often. If it's not as much as we were expecting, maybe we go a little bit longer. It's really kind of playing with timing there and some field experience, but really no data in real time to tell you when that unit is full. And then as far as the efficiencies, like sphericals are comparable to cyclonics in a lot of ways, and the industry keeps getting better, and people keep improving those products. Specialized Desanders has a patent on a low angle tilt sand separator, which you can already tell looks significantly different than the other two, in that we are going to flow into the vessel from the well horizontally, Inside that unit, the gas and liquid are going to be separated. Sand's going to settle out using gravity. And using gravity versus centrifugal force allows us to operate at no differential pressure, also allows us to predict that sand and the behavior of that sand inside the vessel using Stokes' law and managing retention time. And then it also gives us the opportunity, like James said, to measure sand inside the unit in real time so you know when to clean it out. You can see there our sand holding capacity is upwards of 1,000 pounds, and like James said, we have as big as 24-inch vessels that hold maybe 3 times more than that. But the unit does really operate differently, and from this point, want to talk about what makes us different, how this patented process provides benefit to operators and can be implemented really when sand is being produced at any phase of well production to settle out, hunter mesh sand in some of the most challenging environments. So this being a rendering of our equipment, showing you more or less what was on the previous slide. And if you all can see my pointer here, we will flow from the well into the inlet nozzle here at the left side, flowing left to right. From there, about 20 feet later, fluid and gas are taken off of the desander, and in between, sand settles out of suspension, and all that exits the vessel is the gas, oil, and water at the same rate that they enter. This orange box here is our brain center for our Sand Century measurement system, and it is solar powered, and that's going to take measurements off the desander in real time, allowing us to know how much sand is in the unit. And we are able to monitor that via a website or iPhone app, really from anywhere, and manage the process and monitor the process remotely. There is a quick closure. Sorry, I hit my button. There's a quick closure on the back end that allows for access inside of the vessel, taking samples, verifying it's full or empty, and then we have wash ports here at the rear and at the front, which will help facilitate the flush cleanout process. So I mentioned earlier that verticals and sphericals blow down on the fly. Horizontal desanders and slight angle tilt desanders do not. That's because once the sand settles, it wants to stay where it is, and there's not enough energy to move it with simple surging of the vessel. So what we do to clean out the vessel is isolate it. We swap the flow into a bypass unit, typically on location, and then we isolate it, bleed off the pressure, and use a pump to sweep the sand out with high rates of produced fluid. So that's the clean out process, and it's done, like I said, only as needed because we are measuring how full the unit is in real time. Trying to advance my slide here. Here we go. So I mentioned the mechanism to separate sand is gravity. So how do we get gravity to work inside of the vessel? So I liken it to whitewater rapids versus, a wider, deeper stream where you can see the bottom. Inside of the piping, you have gas and liquid and sand all combined into one flow at the speed of the gas. So in whitewater, it's white because there's air entrained in the fluid. This is comparable to in the pipe where gas is entrained in the liquid. As you're flowing through the pipe, it's all moving through together, and we know that these types of rivers can move boulders downstream, and it's the same thing with fluid in pipe in that it moves sand not only out of the well, but then on the surface through the piping. Once it enters the desander, the gas and liquid are going to separate. So we're going to open up into a wider part of the pipe, essentially, create a deeper, larger cross section. So now that gas breaks out of the liquid, just as it does in the picture on the bottom, and in doing so, we can achieve laminar flow and give an environment for the sand to settle out of suspension using Stokes' law. So I'll talk about that on the next slide. But you come up to one of these streams, you can see the bottom, the liquid is clear. The same thing is happening inside of the desander. As the gas and liquid exit the desander, it goes back into the regime in the top picture there. But now sand has settled out and been captured so that when it does recombine, everything downstream is free of sand and non-erosive. And what's excellent about using these fluid dynamics principles is that they're predictable. It's simple physics and understanding the speed of fluids through a pipe. And so, in doing so, we're able to apply Stokes' law. Stokes' law requires laminar flow, which we're achieving through a single phase fluid using a spherical particle and how fast that spherical particle is going to settle out of suspension. So, knowing how fast the gas is moving through at a given pressure and temperature, the viscosity of our fluids, the size of our sand, typically 100 mesh or 148 micron, give or take. We now know how fast that sand is going to fall through those different fluids and when it's going to settle on the bottom of the desander. So the diagram in the bottom right-hand corner shows the trajectory of sand inside the unit. How much gas is being produced at higher or lower pressures, higher or lower temperatures is going to indicate how much volume is moving, in feet per second left to right. And then once that sand hits the liquid gas interface, it's now working in liquids where we know the viscosity and we know the density at pressures at any given temperature. Oil and water obviously thinning out at higher temperatures, making the sand easier to fall and settle on the bottom of the vessel. So our pre-job performance modeling can predict where that sand grain is going to settle. And at lower rates, higher pressures, different parameters, that sand could fall very quickly, or we could have a case where it's settling out closer and closer to the outlet. What's important to know is because of our tilt, the gas head at the top of the vessel toward the inlet is wider and moving through slower. And then as the sand starts to move into the liquid phase and the liquid starts to move toward the outlet, that gets deeper and slower and more laminar. So really the efficiency of the vessel on account of the tilt is made better because you have different things working for you in the right places, and sand is able to settle as efficiently as possible in that environment. Once we get the pre-job parameters and put it through our model, we can tell the client, look, worst case scenario, day 15, this sand grain is going to go about 42% of the way through the vessel before it settles on the bottom. In any other condition, that's a better velocity case than those day 15 numbers, means sand is going to settle out of suspension sooner, and we're going to be equally, if not more efficient in those cases. From that point forward, a sand dune builds more or less centered around where that first sand grain falls, and that sand begins to displace water inside the unit. I mentioned gas and liquid enter here from the left. They split apart, they flow through independently, and then at the outlet, the gas and liquid recombine and exit. So what that means is that we have about 3 barrels of liquid in the unit at all times, and once it reaches that 3-barrel level, then a barrel comes in, a barrel has to leave. Sand comes in and displaces water. We know that sand is heavier than water, and we know the specific gravity of each of those mediums. And so putting the entire unit on load cells allows us to see the entire system gradually getting heavier on account of that 3 barrels being more sand as sand comes in and displaces the water. So again, once it's on location, we take the weight of the system, we start to flow. That entire system comes up to about 15,000 pounds or so. And then at that point, the weight stabilizes. Sand comes in, 2.65 specific gravity. Silica displacing 1 specific gravity. Water means that the weight of the entire system gradually increases. We can take that weight difference and attribute that to sand that's now in the unit in real time. That number and how full the vessel is then displayed on the unit and broadcast onto a website or iPhone app. So now you can see when do I need to clean this desander out? How full is the desander now? Typically, when it gets to about 20 or 30% full, the equivalent of about 550 to 600 pounds of silica material in the unit, it would need to be flushed. And I talked about that a little bit earlier, whereas the system is isolated, depressured, and then flushed with fluid. The whole clean out process takes maybe 15 or 20 minutes, and the well doesn't know anything that's happening because it's being run through a redundant desander that's on location. So I tell people, the name of the game is you keep sand out of this red zone. And if you clean it out in time to where that sand dune doesn't grow into that area, then there's no physical way that sand can exit the vessel, meaning that everything downstream is clean, non-erosive, and free of sand as you're separating those fluids, putting them into the pipeline, and sending them to sales. Talking a little bit more about the data, we are measuring and recording the weight of the desander and the fluids and sand inside in real time. That weight difference I talked about is put onto the iPhone app or website, where you can see how full each of the units that you have in service are, and that determines when they need to be cleaned out. This is particularly important post flowback when there might not be dedicated manpower on location, people managing the field in the area, but not necessarily sitting there or scheduling a time to go over and manage that site. So this gives real-time information for the people that are operating the vessels to know this desander needs to be cleaned out today. This desander is getting full. We don't need to worry about maybe this side of the field as far as sand control is concerned today because these units are filling up slowly and we know we have that additional capacity. And all of that can be pulled up as well. And these charts illustrate the historical data from that sand production to where the gray line here is percent full. And you can see over the course of this day or so time frame that the unit filled up 4 times and was cleaned out 4 times. This gray line being percent full, going from about 4 or 5% to 0, all the way up to about 25 or 30%, in some cases even higher than that. But what's exciting about this is that and you have the data. I mentioned sand production being very inconsistent and unpredictable at times. It's hard to do the guess and check method when on any given afternoon the well could give up a slug of sand like it did here, going from 10 to 22% full in the course of an hour. So having that additional capacity, the ability to monitor, really does give you a lot of information to be as efficient as possible with resources and with how you're going to produce the well, given the phase of production that it's in.
With that, we were able to notify the E&P company that they were taking a frac hit at that time. We do have alarms set on our sand sentry so that if we do see spikes or increased activity, we do get an alarm, which then we can pass on to our partner on location so that they can look into it further. So.
Absolutely. Absolutely. In the cases where some sand slugs come and overwhelm the vessels or start to fill up the vessel very quickly, we can respond very quickly as well. And the good thing is that our capacity being, like I mentioned, 500 to maybe 1,000 pounds of sand before the unit starts to carry over means that in these cases where you see quick increases in the percent full number, our vessels are equipped and capable of handling those sand slugs, and the client gets notified so that they don't go out, 2 or 3 hours later, realizing that their vessel's been overwhelmed and there's been sand carrying through the facility all along, and they were totally unaware. So this also gives us the opportunity to quantify the sand that's being produced. When we do a clean out, you see the unit here at about 30% full. The vessel is depressured. and flushed and then returned back to production. This weight difference before and after the cleanout can be attributed directly to sand that was in the vessel to sand that was then removed from the vessel. Being that the cleanout takes place over a 15 or 20-minute period of time, all else is the same: pressure, rate, temperature, all the other variables are isolated. The only difference is the weight before and the weight after. So this allows us to be incredibly accurate with sand quantification, and it is just silica removed from the unit. And so we're not weighing any water, we're not weighing wet sand on the fly, we're not relying on operators to do that. This is all independent data that is tracked and transparent and independent of any of the other activities that are going on location, up to and including the well production itself. So this really is the most accurate sand quantification on the market, in that before and after that clean out, we know the before weight and after weight, and being able to make calculations at that point puts a very accurate number on what the well is producing in that period of time. So by accumulating that data, by aggregating it, and reporting out a cumulative sand production plot, you can start to see the shape of sand production. You start to see trends, type curves, and different ways that different wells are bringing sand to surface. Allows us to do some predictive modeling, compare to previous jobs that we've done, profile wells by sand production, and then at the end of the day, know with confidence that the well is cleaned up and flowback can be ended. So a lot of times our data will tell the client flowback's over, it's time to move on to the next job, or unpredictably, maybe the flowback's going to last a little bit longer than they were expecting. But knowing that there's a there's a valid reason to continue to spend that money to keep flowback out there or to keep sand control on location means that they're preventing much bigger issues if they were to end flowback prematurely and allow sand production to go through the facility, really starting to cause and really start to cause more critical issues that could stand in the way of the well continuing to produce. So these sand reports are provided in real time, on demand, on the website, and clients can start to see, how is my well performing as it pertains to cleaning up significantly enough to release flowback, or in conjunction with different things that were changed on the frac, different completions methods, downhole tools, other variables. You can now start to see how those decisions affect sand production and flowback, and ultimately the cost to bring the well in line. This being a Permian artificial lift example, we had a client with an ESP in the well, and they wanted to run it basically at the maximum amount of hertz they could to produce as much oil as possible, for that project. Problem was, as they turned up the ESP, they would inevitably take a slug of sand to surface, shutting in the well, and they'd be starting all over. So what we were able to do is deploy Desander onto these wells, each one Desander per well, and they started to increase their ESP and increase their oil production. In doing so, they could see that going from 49 to 50 hertz, really had no effect on sand coming to surface. The VP of operations made the call: we're turning this up, and we're not seeing sand really affected. So let's go ahead and increase production and increase the pump downhole. When they went from 50 to 51 hertz, everything changed. So you can see immediately they started to bring sand to surface. They took 2 sizable sand slugs, both of which were caught in the Desander with no interruption to operations or production. And from that point forward, they were able to let that sand subside and continue with increasing the VSD until they were able to get to 53 hertz, where when they turned it up, they saw a slight increase in sand production, but that quickly leveled out. And they knew at that point we're at the production rates we want to be at. You know, we've gotten the information we need to know and have confidence in the fact that this rate is not going to produce sand. So that Desander got moved on to another project, and the client could move forward without any sand control, comfortable that the rates at which they were producing were going to be effective, and that there wouldn't be any damage to facilities or anything unexpected in the way of sand production for the remainder of that project. And then talking a little bit about emissions, one thing I mentioned is that slight angle tilt or horizontal desanders do not blow down on the fly. And that gives us a lot of options. So in cleaning out the desander, it is isolated from the well during that process. And in doing so, we have about a barrel of trapped gas to manage. So having that situation means that we can take that barrel of gas and we can direct it to a number of different processes. Some clients elect to depressure it to atmosphere. It's a minimal amount of gas, done so infrequently, and in doing so, they reduce their emissions probably 85% over the process of blowing down every 15, 30, or 60 minutes with a live well flowing to an open top tank. Some clients have gone the next step in blowing down to a flare where that methane is burned off as CO2, 1/25th the greenhouse gas impact versus methane. And then with that, they've gone 99.5% of the way to emissions-free operations during their flowback. One client allowed us to blow down into a pressure vessel and then direct that gas to their tank battery, which was equipped with a VRU or an emergency flare. But under the normal operation of that facility, we would depressure the desander, the gas would go to the tank battery, and 100% of that gas was boosted back into the pipeline and sent to sales. So this was a true emissions-free, totally closed-loop flowback with no gas, no methane, no CO2 released to atmosphere. And in doing so, complying with New Mexico regulations, some of the federal regulations that we all know that situation there, how they come and go, it seems. But with operators that are looking to close their entire operation, spend a lot of money retrofitting facilities to get rid of valves and other pieces of equipment that release gas to the atmosphere, getting a zero emissions flowback is the next step in achieving that goal. And specialized desanders in our horizontal vessels really give you the only option on the market to to minimize the amount of gas released, and then give you options with how that gas is released, so that you don't have any methane or CO2 emitted to the environment. And with that, this slide is essentially a summary of how you can increase operational efficiency to maximize well production in the process. All of this we talked about, and all the different variables and value that we can bring to the operation mean that you're getting data, you're controlling emissions, you're using your manpower in the most efficient way possible, and you're also stopping the vast majority, if not all of the sand produced from the well, meaning no damage to equipment on site, predictability in operations, and ultimately better long-term production from your oil and gas wells. So with that, we thank you very much for attending our presentation. Look forward to answering any of your questions, and certainly we're excited for this opportunity, and thank you to Ahmed and PioPetro to giving us this platform in order to tell all of you about our technology and the value we bring to the oil field. Thank you.
Thank you. An enlightening session by James Evans and Anthony Sisto, the president and vice president of Specialized Desanders. It was a pleasure having you with us at Permian Tech Talk. We will now move over to answering some questions from our audience.
Jomana, there is many questions I left you on your Facebook Messenger.
Yep. Kofi Kwame is asking about the main selection parameters of.
Sorry, what was that?
Oh no.
Are there selection parameters of desanders?
Yes,
Selection.
typically what we do is we try to get your flowing parameters, and then we take those and we put them into our in-house computer program to determine which size of desander would be the most efficient for your application. So typically what we're looking for is shut-in pressure to make sure we meet those standards. And then we look at worst case scenario, your highest flowing rates, liquid and gas, with your lowest pressures. And then that would typically give us the worst case conditions. And then we can, like I said, put that into our program and see which desander would be the most effective.
Absolutely. And the great part about that is that we know before we go. So the worst thing is to put out a piece of equipment, hoping it works. And when it doesn't, well, what do we do? Do we get another one? Do I need a different one? All of that is wasted time, movement, and money. So with our performance modeling and being able to use physics to predict the efficiency of our vessel, we can tell clients, look, one unit's not going to handle it. You need to split the flow. And before that job happens, but those are extreme cases. In the vast majority of cases, we have big enough, long enough, higher pressure rated enough units to meet certainly every well in the Permian Basin and most other basins as well. Going up to 10K for some applications. 10,000 PSI.
Yes, we have a range, many different sizes of desanders, as I mentioned earlier in the session. First desander was 8 inches by 10 feet long, and now we go up to 24 inches, 20 feet long, with pressure ranges 1440 all the way up to 10K. And we have custom built some desanders for clients in the past as well, to try and fit or make sure that we do fit the client's needs.
That's awesome. We have another question about drilling fluids and completion fluids. Is there any mud preference that can enhance or improve the efficiency of your devices?
Well, when it comes to completion fluids, what works to deliver sand into a formation is what will work against settling sand out of suspension at the surface. So what's important for our process is that the fluid that comes back is broken of viscosity, or either that, or if we know the viscosity, then we can be prepared for that. Also, emulsions can stand in the way of sand being able to settle out. We're using gravity, so there's really no magic to it other than a fluid of a particular density allowing sand to settle out of suspension. So as you can imagine, it's harder to settle sand out of salad dressing than it is out of coffee or water. So some of those same dynamics apply when it comes to completions fluid. Drilling fluid, probably less of an issue for us, because by that point, we're not seeing any of that at surface with the oil and gas production. So completion fluid is more of a concern. Emulsions at various pressures and temperatures are a concern. But the vast majority of that we can mitigate or be prepared for and design the job accordingly.
And with our product there, as Anthony mentioned, it's not magic, but there is a little bit of magic behind it. We do not have bags or screens or filters inside. As Anthony mentioned, we are allowing gravity to work. So, yeah, the way our product is designed, our desanders do not erode. The very first desander that we built in 2001 could still be put in service today. So our desanders do not wear out. They do not have any moving parts inside.
Got it. And another question was, any known operational limitations and constraints to that technique?
So I mentioned emulsions being something that needs to be prepared for, and anything that stands in the way of that sand falling is something that obviously we need to know before we go on location. But other than that, we're looking at the velocity of the fluids passing through the vessel in the first, maybe 30 or 60 days, longer in some cases. But the limitation really is, how much gas can you handle at X temperature and pressure, looking at oil rates, water rates, the temperatures associated with that, and how that affects the viscosity depending on the API of the oil. And then at that point, we're just talking about time and an environment to make sure that sand hits the bottom and stays there. So really, there are limitations when it comes to water rate, total fluid rate, things like that. Certainly gas rate, there's limitations to that as well. They're going to offset, so lower the gas rate, the more liquid we can handle. But that's where this model really comes into play, where you're going to know, and we're going to tell you before the job that the vessel we're sending out there is adequate to stop the sand during that worst velocity case. At that point, once you hit line pressure and you're flowing and the well's declining, it gets easier and easier and easier every day that progresses. So we're really looking for what's that peak velocity case, and from that point, we handle everything before and after that scenario. So I'll tell you, we have, records when it comes to how much liquid we can handle. We're talking about 9,500 barrels of total fluid per day. At line pressure, something like 23 million in gas per day. But again, those are really just checkpoints, and that if you have 5,000 psi of flowing pressure, we're now handling several dozen MCF per day, maybe upwards of 36 or 40 million. So really, this model is going to determine that. And every well is different. Every case is different. The goals of each client are different. And so we take all that into account, including our real world experience, to build in some safety factors and some other knobs and dials that can be used to make sure our prediction is valid and something you can rely on once the unit's deployed.
And sometimes those cases are for a single unit. We design it on paper before we go to the job, and that's where we can see if a single unit won't handle it. Maybe we have to put 2 units in series or in sequence. So that way we can we know what we're going to be handling when we get out to location.
Mm.
That's awesome. And there's always limitations to any technique, but it's good to take the risk assessment into consideration first. So we have another question about the zero emissions part. How do you ensure that it's zero emissions?
Okay. So I'll get to that slide here. Sorry. So ensuring that it's zero emissions really is fundamental to the process that you're using. So the well's flowing through our desander. That's a closed system. Downstream of the desander, it's flowing to facilities and flowing to separators and all of that. Operators have zero emissions into that system, as evidenced by the VRU that takes the vapors off of that tank and puts it into the pipeline. Our process only requires that a barrel of gas be directed during our clean out process. So verticals and sphericals blowing down on the fly, that means you're opening a valve, you're flowing the well directly to a vessel, which in most cases is an open top gas buster tank, or some vessel of sorts that needs to have a pop off on it or a flare, because you have the risk of well pressures hitting that system. You don't have the risk of well pressures hitting our system uncontrolled. So you choke downstream of the desander, gently putting that barrel of gas into a pressure rated vessel that you see here. And then from that vessel, you're able to carefully direct that gas to the tanks where you have a significant amount of capacity for gas to expand again. And then once the pressure is seen in that system, the VRU automatically kicks on and lowers the pressure of those tanks by putting the methane into the pipeline. So, verification of zero emissions is really fundamental to how you're managing the gas. There's no risk of release. There's nowhere for it to release. And with the process itself, all gas is directed to sales.
And the way we set up the operation with the client, showing the picture on this location here, it's a 3-well pad, but we have a bypass unit so that we can isolate that single desander and safely blow it down at a controlled rate to the other pressure vessel on location, like Anthony had mentioned.
Right, without any interruption in the well flowing through a sand control vessel, and with no holding back production or surging the well, conversely. So the well doesn't know anything. It's flowing as naturally as possible throughout the entire process. And we're just doing our part to send that gas to sales.
That's awesome. Now, a question I had was, with the sand volumes, you get different particle sizes, and that can vary significantly. How does your system adapt to the fluctuating sand loads without compromising the performance?
Sure. It's a great question.
Typically, when we meet with the client ahead of time, we try to find out what size of sand they are anticipating to come back. So then we will put it into our pre-job planning, and we will put that number into our computer program, which then allows us to determine which desander may work the most efficient. So we can adjust the efficiency of the desanders. On the slide here, it's showing 100 mesh, but we can make that size of sand smaller or bigger, and then which will then change the calculation summary of the desander. So if we're finding that the sand particle is coming in a lot smaller than we anticipated, it will flag it in the program so that we can adjust and possibly send a bigger desander out before the job even starts. And we have been on other jobs where the client is expecting 100 mesh or 150 micron sand, but yet we know that the sand does get pumped in at high pressures and it does crush. So we have seen it where we're getting 100 mesh, but we're also getting a lot smaller particles caught in the desander as well. So sometimes we do particle analysis to see what we are catching to provide to the client.
Yes, absolutely. And like James said, we're going to assume the smallest particle size in our pre-job performance modeling. And so larger sand is going to settle out faster than that. So we do take the worst case scenario when it comes to the smallest particle size. When we design the job, we also look for a cutoff of about 50 or 60% of the way through the desander. We don't design jobs where the sand is falling out close to the outlet. That gives us that additional level of safety. If we do see some smaller particles, if we do see some slugging, if we see some viscosity in the fluid that we weren't prepared for, we're going to send out a unit that's more than adequate, given the parameters, with some additional capacity and additional functionality to catch smaller sand grains or sand during conditions that are less favorable to that sand falling out of suspension. So no, we really do build in for every case we can think of. But obviously, the more information you know before you go, the better prepared we can be and assure that the right unit's deployed.
And we know on some wells it's new and they don't know. So then we oversize. We work with the client and say we're going to give you our biggest, baddest units, and we'll monitor things as we go, and we'll both learn something at that time.
Always great to have some extra safety margin.
Definitely.
Now, the system is promoted as having no pressure drop. What design elements eliminate differential pressure, and how is this validated in field operations?
Sure. So there's no pressure drop because we have a 3-inch inlet, a 3-inch outlet, and then a 20 or 24-inch vessel in between. So there's no difference in the size of when the gas enters or when the liquid enters to when it exits. It's just expanding temporarily between the inlet and outlet nozzles. So obviously this can be verified with upstream and downstream pressure gauges. We have done that. I say no differential, probably maybe 10 psi, essentially whatever pipe friction we're seeing, during that process. But um, conversely, verticals and sphericals utilize pressure differential, are designed to achieve a given pressure differential, and they use that to push sand and create centrifugal force to separate sand out of suspension. This can be detrimental to the well and the production that you're able to achieve. So especially with older wells in the life of the well, as pressures decline, and you may only have 200, 300 pounds of flowing pressure to work with. If you're going to take 50 to 100 of that for your sand control process, that's now back pressure on the wellhead that's going to hold back oil production. We did have a client in North Dakota that was using a cyclonic on a gas lift well. Um, it was very difficult because they were pushing against the differential that cyclonic required in order to settle sand out. And if they didn't achieve that, then they weren't settling, they weren't separating sand, and they were having issues downstream. We replaced that vertical cyclonic, reduced back pressure on the well by 50 pounds. They saw 50 barrels a day more in oil production. So it was a one-to-one, direct correlation between dropping, dropping that wellhead pressure, and then being able to produce the wells more efficiently and achieving, higher sales.
Perfect. And another question about keeping track of everything. So do these units have a built-in monitoring system or digital integration of some sort?
Yeah, so we do have our own monitoring system. The Sand Century system I talked about, where all of the calculations are done on site. They're solar powered and all self-contained and intrinsically safe. We can export that data to SCADA and tie it into operator SCADA systems. It's also put up onto a secure website that the operator can access. The iPhone or smartphone app is also somewhere that you can monitor that data. So as we're collecting it, doing our calculations, making, analyzing that data, doing reporting, things of that nature, it's all contained there on our website. But then the raw data itself can be exported to SCADA, and some of that can be recreated for the client to do it directly into their system, tracking it alongside different production curves and other bits of information that they want to correlate. So hope that answers the question. But as far as connectivity to that, like I said, it's typically beamed up via cell modem. We do have SAT modem capabilities or direct tie-in to SCADA on site into the client's data acquisition projects.
Awesome. Last but not least, we were hoping to get a little bit of an inside scoop for the Permian Tech Talk. What advancements are you currently working on to further improve desanding efficiency or adapt to emerging ESG regulations in oil and gas?
Yeah, oh, go ahead, James. You can take that.
Sorry, Anthony, I'd cut you off there. As we continue to work in, one of the most challenging basins, but exciting basins is the Permian. We continue to develop new products. We are currently working on some other sand measurement detection devices internally. And then as the world continues to take on and develop AI, we are working on some in-house programs on that with AI. So maybe one day we can predict how much sand your well is actually going to be producing. But those are some of the exciting things that we're working on currently with hopefully to be released possibly later this year or even into early next year with some of our new products.
I'm sure that's going to be great news for many of our audience here. Great session by James Evans and Anthony Sisto, President and Vice President of Specialized Desanders. It was a pleasure having you on Permian Tech Talk with us, and great thanks to Specialized Desanders for being the second company on this series, Permian Tech Talk of 2025. James Evans and Anthony Sisto, thank you so much for joining us today, and thanks everyone for tuning in.
Thank you very much for having us.
Thank you.